governing relation, if I follow your lead, and I like what your idea is. So this is the governing relation. A is what? It's the square root. B squared plus C squared, right? B would be what? A squared minus C squared, right? And C, of course, is the square root of A squared minus B squared. Ah, cool. So this indeed this gives us what down here? Following our generic idea, this would go to what? B is, sorry, I'm processing. 4x squared plus 9, which of course is the thing we're trying to remove, right? Thank you. This was a fantastic comment. I am very, very happy you spoke up.
Then how do you get the
Over 3. Well, the Koch phi, right? Adjacent over hypotenuse, which is this over 3. Cool. The thing we got to be careful about is it's not governed by the Pythagorean theorem. The relation between the Koch and sinh is the hyperbolic identity. And this is probably why it's not in most textbooks, to try to explain how this is different than the triangle thing, because everybody wants to teach the triangle thing for sine and cosine. That's easy to understand, right? Because it's just regular sine and cosine, and you're kind of used to that. This is something kind of weird. But, all right, getting back to my larger point. So, by the way, so this kind of answer, like suppose that you had put inverse hyperbolic sine of 2x over 3 in for just phi here. You'd have sinh of twice the inverse hyperbolic sine of 2x over 3 plus 9/4 inverse hyperbolic sine 2x over 3 plus c. That would still be an okay answer, right? This business of simplifying this to that, you know, maybe that's 20% of the credit. I'd still give you like 80% credit if you could just do the start of it. This last part, we're really dealing with the difference between an A solution and a B solution. All right, this is the harder kind of. A significant partial credit would be given for just getting halfway through this problem, is what I'm trying to tell you. So, but grading aside, this is really, really easier than the trig substitution here, right? Secant cubed versus Koch squared. Well, Koch squared is way easier. And we still get a pretty nice formula. Look at the difference in the formula. So here we have, these formulas look really different though, don't they? Look at this. This x times the square root of 4x squared plus 9 plus the inverse hyperbolic sine of this versus, here you can look at them both at the same time. So on the one hand, I mean, they both got this x times root, right? But this is inverse hyperbolic sine of 2x over 3. Up here we've got natural log of this. Those are actually the same, though. Remember the identities back in section 7.9, theorem 7.9.2? It told us that we can write inverse hyperbolic sine in terms of a natural log of certain algebraic functions. And when you use that theorem on this, you'll find that this and that are actually the same expression. Hey. All right. I have a few more examples in here. Let's see here. Let's see here. We could derive the area of an ellipse if we wanted to. And then we'll get the partial fractions. Now I'm going to put this away. Is there some question from the notes before I put this away? But mostly I just wanted to show you that pair of examples. That's See, I gotta save this. Do not erase. This I must leave. Tell them to not look at. Just avert your eyes for the start of the next section lecture. Sorry, I think it's funnier to me than you guys. But let's see here. Another example. So the integral of, let's see here, I just did do something like this. This may be unpleasant. We'll try it out though. X dx over the square root of x squared plus 2x plus, let's see here, $13. No. 11. All right. This is kind of like the problem the gentleman asked me about at the start of class that I postponed till now. So these trigonometric substitutions, these are almost directly applicable to a Y class of problems where we don't have an X term. But if you understand completing the square, we can extend the reach of these substitutions to problems that also have an X. So what you have to do is you have to see how to write this again as a sum of squares. This is by the completing the square technique. So basically the algebraic thing to do is that x squared plus 2x plus 11, you see by the technique of completing the square, is exactly x plus 1 quantity squared, right? Which would give me back what? This gives me back what? This gives me back x squared plus 2x plus 1, right? Agree? Maybe you had some algebra teacher in high school or something who taught you this 9-step process for completing the square or something. There's an algorithm. You do these steps. I would discourage you from this way of thinking. You should think about what the goal of completing the square is. The goal of completing the square is to rewrite this expression as a square plus another thing, the square containing the variable. So to get the x squared, I have to put x. To get the 2x, I have to put 1 here, because when I square this out, I get this. Okay, fine. The algorithm is you have to divide this number by 2. I will admit it. But common sense also tells you that. So x plus 1 squared. Now, when we do that, I've added 1 by writing this, right? I have 11 here to start with. So how many do I have to left? I still have 10 more to add, right? So plus 10. And that's how you complete the square. Check your work by working backwards. If I multiply this out, I get back there, right? If you're not super comfortable with that, you're probably not alone. And that's okay, but it is something you need to learn. Okay, so x plus 1 plus 10. Oh man, plus 10. I wanted to add 10, not 11. I will take my medicine and deal with not having a nice thing there. 10 is what? The square root of 10 squared, right? Now, okay, so now we're good to go. We can go, aha! Square root of a sum of squares. You're in my house now, and I will subjugate you with a tangent substitution, right? No subjugating the expressions. No. Oh. It's too early for jokes, I guess. I don't know. All right. You say they're not jokes. Fine, they're not jokes. Caught me. talking to a human or an animal? I don't know. Oh, cute little puppy. Oh, that's it here. That's it here. Sorry. So, I mean, there's different ways to go here, but the greediest way to do it, I'll be greedy, would just to be say, okay, so I'm going to say x plus 1 is equal to the square root of 10 times tangent theta. Actually, I'll take a vote. How many of you want me to do this? How many of you want me to make a u substitution first and then do that? U substitution.
Is that easier?
I don't know. I mean, I don't know. I mean, that's a harder question for me to answer. I'm going to stick with this and see what it does to us. What's x plus 1 squared then? It's 10 tangent squared theta, right? So x plus 1 squared plus 10 is equal to 10 tangent squared theta plus 10, right? AKA 10 secant squared theta. Which is pretty awesome. Now, this is equal to what? Integral of, I'm going to do one step here. X, what's the dx? Square root of 10 secant squared theta d theta, right? And I'm dividing by the square root of 10 secant squared theta. Now, can you just ignore x and just go on with your life? Is that like a viable thing to do when you're integrating? No, it's not true this morning, and it's still not true on your test. Do not ignore the x. Ignore the x to your peril, right? You need to deal with it. How do you deal with it? You need to convert x to theta. How do you do that? X is equal to what? Square root of 10 tangent theta minus 1. So what do we have? We've got square root of 10 tangent theta minus 1 parentheses times the square root of 10. And, oh look, so that's going to give me what? So fine, I'll do one more step. Secant squared theta d theta. And then I'm dividing by what? Square root of 10 secant theta. So the square root of 10's cancel. What are we left with? We're left with square root of 10 tangent theta minus 1 times secant theta d theta. It's kind of scary looking. Don't be too afraid. We will put it in its place here. This is minus the integral of secant theta d theta. We know how to do that one, right? Plus the square root of 10 integral of tangent. Oh, integral of tangent secant. I was about to do something for that, but then you guys would justly have made fun of me. We shouldn't be working to do that integral, right? What's the integral of tangent secant? Secant, right. Now the first one is monstrosity, but there it is. Natural log, the absolute value of secant theta plus tangent theta plus the square root of 10 times the secant of theta plus a constant. All right, so we're going to use the triangle. This time the boring trigonometric triangle. What do we have? We've got tangent theta is what? Tangent theta is x plus 1 over the square root of 10. So I can use the adjacent side as square root of 10. The opposite side is x plus 1. And what's the hypotenuse then? Square root of what? X plus 1 squared, right? there we go. We're back to what we completed the square on to start with. And so this little triangle here shows me that secant theta is what? Square root of x squared plus 2x plus 11 divided by the adjacent side, square root of 10. And the tangent theta we already know. So lo and behold, here's the answer. Minus the natural log of the absolute value of the square root of x squared plus 2x plus 11 divided by the square root of 10 plus tangent theta, which was what? Plus x plus 1. Oh, look at that. That common square root of 10, we could move that out of the answer, couldn't we? Plus the square root of 10 times the square root of x squared plus 2x plus 11 divided by square root of 10. That's the secant theta plus a constant. We can clean this up. Let me give that a name. I'm going to call this integral I. So what I'm writing here, we shouldn't write floating expressions. I mean, this is the integral again. All right. So the integral then is equal to, you can factor out 1 over the square root of 10. So just by adjusting the meaning of the constant, we can pull that out of the natural log and just write minus the natural log of the square root of x squared plus 2x plus 11 plus x plus 1, absolute value on that stuff, plus the square root of x squared plus 2x plus 11 plus a constant. And there you go. Sorry, I seem to have gone over time. I will shut up. So. Thanks, guys. You can cut it off. Let's press the button again.